Hey there, and welcome back to another Papetti Math YouTube video tutorial where I'm going to be teaching you, yes you, Algebra 1. And in this video, we're going to be taking a look at exercise number 3, where we're going to be looking at tables and comparing whether it represents a linear or an exponential function, and then we're going to write the function that represents each table. So let's get right into part A right here, where we have this table. And we always want to check our x values and make sure that they're going up by 1. Because if they're not going up by 1, we're going to have to use our average rate of change formula instead of just looking at our y values. So now we want to look at our y values, or our f of x values in this case, and see if there's a pattern going from one to the next. And is there a constant pattern? Well, the first one you might see is, well, we subtract 60. Do we subtract 60 again to get 30? And no, we don't. So we're not subtracting the same amount over and over. So that means chances are it's not linear. So now we look, and how else can we get from 120 to 60? Oh, well, 60 is half of 120, so we can multiply that by 1/2. And 30 is half of 60, so we can multiply that by 1/2. 15 is half of 30, and 7.5 is half of 15. So each time we increase by one x value, we are having half as much in the y value. So we have, in fact, enough information here to write our exponential function, which again, the general form is y equals a times b to the x, where a is your initial amount, where x equals 0. So we know our initial amount is y equals 120 is our initial amount, times our growth or decay factor, which in this case is 1/2 to the power x. The only thing we might want to change there is we want to change that y to an f of x, because it says that's what we want to be using in this table. So now that we have that, let's go ahead and let's take a look at the part B. But again, we have f of x is equal to 120 because that was our initial amount, 1/2, which was our decay factor. It's decaying by half as much each time to the power x. Taking a look at part B now, again, we're looking at our x values. They do go up by 1 each time. Okay, so f of x now looks like it has a pattern. Let's figure out what that pattern is. And we go from 1200 to 800. We could subtract 400. 800 to 400, well, that's minus 400 more. 400 to 0, well, that's subtracting 400 again. And 0 to negative 400. So we have a constant rate of subtracting 400 each time. So this is going to be represented by a linear equation because we are subtracting a constant amount every time. So linear equations often look like y equals mx plus b, where m is our rate of change and b is our y-intercept. And we have both of those in the table given to us already. So we know our rate of change is going to be negative 400 x, and we know that our y-intercept is where our x value is 0, so that's going to be a positive 1200. And again, the only thing I'd want to change about this is I want to change my f of x, my y here to an f of x. And also in my final equation. Okay, so my final equation is f of x is equal to negative 400x plus 1200. Let's look at part C now. Part C, we have 0, 1, 2, 3, 4, and then we're going from 50 to 55 to 60.5 to 66.55 to 73.205. And we could tell that this is not adding the same amount, so we are multiplying by something here, but we have to figure out what that something is we're multiplying by. So if we don't know right away, if it's not easy for us to see, what we can do is we can do 55 divided by 50 and see what that gives us. And if it's the same thing that 60.5 divided by 55 gives us, then we're on the right track. But we'd have to check 66.55 divided by 60.5 and also 73.205 divided by 66.55. If you put each of these into your calculator, you will find that they do give you the same amount of 1.1 each time. So you get 1.1 every time you divide those, which means we're multiplying by 1.1 every time we increase by one x value here. So that's going to be our growth factor. So again, we're going to set up that equation of y equals a times b to the x, since this is multiplying, this is an exponential function. When we create our function, we're going to have f of x instead of y is equal to our initial amount, a, which is 50, times our growth factor, b, which is 1.1 to the power x. So right here is the equation that represents the values in this table, which brings us to our last one in this exercise, which is part D. And now we're looking at our x values again, and we want to notice that our x values are going up by 1, 2, then 4. Okay, so our x values are quite different here. So if you just went by your y values, you'd notice that they're going up by 2, 4, 8, 16, 32. The y values are doubling, but your x values are not going up by 1. So we want to be careful with that, because just by looking at your y values, you might think right away it's exponential. But it's not the case, because our x values are going up by different amounts each time. So what we're going to have to do is we're going to have to find the rate of change for each of these set of points. So we'll start with 0, 2, and 1, 4. So we're going to find our change in y over our change in x. And we're going to see what our rate of change is. So we're going to have 4 minus 2, that's our change in y, over our change in x is 1 minus 0, and we're going to get 2 over, 1 minus 0, excuse me, and we're going to get 2 over 1, which is 2. That's going to be adding 2. Now let's see if we're going to have that same change in y over here. So we're going to take our change in y, which is 8 minus 4, to get from here to here. So this is 8 minus 4 over 3 minus 1 is our change in x. It's going to be 4 over 2, which also happens to be 2. We're going to check it out from here to here. So we're going to have 16 minus 8 over 7 minus 3. That's going to give us 8 over 4, which also happens to be 2. And finally, we're going to have 16 to 32. So that'll be 32 minus 16 over 15 minus 7. And our rate of change there is going to be 16 over 8, which also gives us 2. So our rate of change is constant by adding 2 every time. Another way to look at that is that we have 0, 1, we're missing the 2 value here, 2, 3, we're missing 4, 5, 6, 7 there. And if we're going up by 2 every time, we could check that that works by going 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we are going up by a constant amount of 2 each time, so this is a linear equation. So that's going to be in the form of y equals mx plus b. We just found that our slope was going to be 2, so that's 2x, and our y-intercept right here is also going to be a positive 2. So we have a equation of y equals 2x plus 2, but again, let's change that y to f of x to match the variables in our table. So f of x is equal to 2x plus 2 in that final table below. And if this video is helpful in setting up a linear or exponential function based on a table, please give it a thumbs up, and you're now ready for exercise number 4. Thank you for watching.